People have been arguing for centuries that 0.9 recurring can't equal 1. This might be because we can produce a pretty good argument against any proof that 0.9 recurring equals 1. And we will examine one of those arguments now. Consider a right-angled triangle with two equal sides of x pixels. The long side, or hypotenuse, should measure the square root of 2x squared pixels, according to the Pythagorean theorem. But this can't happen, because any line on any screen will consist of a whole number of pixels. And so we can't actually draw a line that is exactly the square root of 2 of any unit of measurement. All we can do is draw a line that is close to some value in the sequence of values generated by a square root of 2 algorithm. Such an algorithm can't complete. It can't do an infinite amount of work and say, there you go, I've produced a constant that is the square root of 2. Unlike 0.9 recurring, there is no constant that we can say the sequence is approaching. So the supporters of real numbers have to dubiously claim that they can imagine a final constant, and since they think they can imagine it, such a point must therefore exist. And so, even some mathematicians now finally concede that the square root of 2 does not exist. If the sequence corresponding to an irrational number has a constant value which we call a limit, then the decimal representation of that number must contain an actual infinity of digits. And surely any actual infinity is absurd. How can there be no last non-zero term, and yet the sum of the terms is somehow a static value? It doesn't make any sense. The 0.9 recurring equals 1 debate won't go away while blatant absurdities like this one remain unresolved. This problem was even debated by the ancient Greeks. It was about 500 years BC when the ancient Greeks proved that the square root of 2 could not be expressed as a rational value. We are not sure who devised that proof, but it is usually attributed to Hipparchus of Metapontum. Hipparchus was a Pythagorean philosopher. The argument involved line segments and was referred to as incommensurability. The proof could have been interpreted as evidence that such lengths can't exist, especially because the Pythagoreans wanted to believe that everything could be expressed in terms of rational values. But it seemed more reasonable to them to accept the existence of irrational lengths, and that this amazing information was previously only known by the gods. Another prominent Greek philosopher to talk about unending series was Zeno of Elea. Zeno's starting position was that motion is continuous, and his objective was to show that motion is an illusion. So he devised several paradoxes to show that continuous motion leads to absurdity, and many of his paradoxes involved unending series. For example, his most famous paradox is a reworking of the even older fable of the hare and the tortoise. It is a race between Achilles and a tortoise, where the tortoise is given a head start. By the time Achilles reaches the point where the tortoise started from, the tortoise will have moved on. So Achilles then needs to reach the new position where the tortoise has moved to. Every time Achilles reaches where the tortoise was, it will have moved on to a new position. This could go on indefinitely, and so it appears Achilles would need to complete an infinite number of tasks if he is ever going to catch up with the tortoise. And surely it is impossible to complete an infinite number of tasks, isn't it? Next up we have the Greek philosopher Democritus. Zeno's argument was that motion must be an illusion because it leads to absurdity. And Democritus agreed that motion would lead to absurdity if it was actually continuous. But Zeno's paradoxes could easily be solved if motion was not continuous. And since the concept of continuous leads to absurdity, Democritus concluded that nothing could be continuous, and everything must consist of a finite number of indivisible parts, which the ancient Greeks called atoms, and so this belief was called atomism. If the atomists were right, then everything must consist of smallest parts, including anything real or imagined, and that would include any geometric construction such as a line segment supposedly measuring exactly the square root of 2. But fiercely opposed to the atomist viewpoint was the rich and influential philosopher Plato. Plato's alternative was a realm of perfect forms, distinct from the real world in which we all live. His theory of forms became known as Platonism, and he founded a large academy which became the birth of all academia, through which Platonism has thrived and atomism has mostly been disregarded. If we accept that a length of exactly the square root of 2 can exist, then it follows that 9/10 plus 9/100 and so on should also correspond to a static fixed length. In which case a journey from A to B should be able to be considered as being a completed infinity of smaller journeys. So when we get past point B, we will literally have gone to infinity and beyond. But just because we know it's certainly possible to move from point A to point B, it doesn't mean that the concept of a completed infinity is the right way to model that journey. The argument that it appears to be successful can't be considered to be a valid argument for using infinity in mathematics. You might expect mathematicians would know better than to use this invalid argument, but they still do. Finally, thank you for taking the time to watch, and I hope you enjoy my other videos.